Why would I be interested in studying sequences?
Well, to me, I think it seems like one of the important reasons we study sequences is to understand certain real numbers, which are difficult to understand.
How can we understand real numbers using sequences?
For example, take the number pi, right? So what is pi? Pi is the ratio of the circumference of a circle to its diameter. And this is the same no matter, where you draw the circle. So long as you draw a circle on a plane, the ratio of the circumference of a circle to its diameter is always the same. And that number is defined to be pi. And that is not a rational number. It's not like, 22 by 7 as we often say. It's a real number, and it's not so easy to get a very good approximation of it. But amazingly, 1500 years ago, almost, Aryabhatta, he actually found a pretty good approximation for it. He said that pi is, let's see, 62,832 divided by 20,000. It's a pretty good, accurate approximation. I checked; it's accurate to about 2 parts per million. And I think he may have used a sequence that converges to pi.
A sequence that converges to pi, is that easy to find?
Well, there are some well-known ones. I don't know if you'd call them easy to find. So one really fairly simple and nice one is 4 times 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9. You get the idea, right? You keep writing 1 divided by odd numbers with alternating signs and multiply by 4.
Why do you call this a sequence? I don't see a sequence of terms here. It seems like a sum or difference of terms.
Fair enough. I mean, this is, I guess you could call it an infinite sum. But we can actually think of it as a limit of a sequence. Let me write down a sequence that corresponds to this. So I'll take A1 to just be 4 into 1. I'll take A2 to be 4 into 1 minus 1/3. I'll take A3 to be 4 into 1 minus 1/3 plus 1/5, and so on. And what we are saying is that the limit as n tends to infinity of an is equal to this magic number pi.
Is this the sequence that Aryabhatta used?
Well, you can use this to compute pi, but I don't think this is what Aryabhatta used. This one converges very, very slowly to pi.
Do other real numbers also have sequences which converge to them?
Indeed they do. I have a favorite in this matter, and it uses the idea, it's used a very beautiful idea, the idea of continued fractions.
Continued fractions?
Yeah, you remember in school how they would give us a fraction and ask us to express it as a proper fraction or something like that?
Yeah, sure, I remember. 3 by 2, you had to rewrite it as 1.5 and so on.
Exactly. So, what you do is you start with your improper fraction, you subtract from it the largest integer that is less than or equal to improper fraction, and then you're left with a proper fraction. Right? Let me show you a slightly more interesting example. So you have 41 by 29. Right? So what's the largest integer that's less than or equal to 41 by 29?
So 1.
1, right? And so 1 plus, so 41 minus 29 is 12, I guess. 12 by 29. Okay, so this is a fraction. Now you continue.
Okay, continue. What do you mean by continue?
Yeah, so this is a proper fraction, but the clever idea here is that 29 by 12 then is not going to be a proper fraction. So what you do is you take this 12 by 29 and instead write it as 1 over 29 by 12, right?
Okay.
Now 29 by 12 is not a proper fraction, so I try to express it as a proper fraction. So what I get is 1 plus 1 over, and so 12 goes into 29 2 times, so this will be 2 plus 29 minus 24 is 5 by 12.
Okay.
Okay, I hope you are still with me, and so now see continue, right. So what I do is this 5 by 12 I write it as
1 over 12 by 5.
exactly. So I get 1 plus 1 over 2 plus 1 over 12 by 5, and then I do 1 plus 1 over 2 plus, and what is this, 5 goes into 12 2 times, so I get 2 plus 2 over 5.
Right.
And let us see, continue again, and I get 1 plus 1 over 2 plus 1 over, oh this is getting long, 1 plus 1 over 5 by 2, right, and 5 by 2 is just 2.5.
Okay.
So I got this, right. So let me just bring that down. What was this we started off with? We started off with 41 by 29, and we got this what is called the continued fraction expansion of this rational number 41 by 29.
Okay, why would you want to do this? I mean, it seems like a very complicated way of writing that fraction.
Yeah, and also what does it have to do with square root 2 or whatever, right, with irrational numbers. So the now comes the even cleverer part, which is that you can do this algorithm, this step by step procedure that I described. You don't have to start with a rational number, you can start with any number. So let us try to do this for square root of 2. Okay, so look at square root of 2. Okay, so we know that square root of 2 lies between 1 and 2, because 1 squared is 1, 2 squared is 4, and so square root of 2 has to be somewhere in between. So 1 plus, so this number square root 2 minus 1, which is somewhere between 0 and 1. So this is now what we think of as a, well, it's not a fraction, but it's a number between 0 and 1. So what I can do is I can write this as 1 plus 1 over root 2 minus 1 inverse, or if you wish 1 over root 2 minus 1. Okay, now we need to do a little bit of calculation here. Okay, so let us look at this 1 over root 2 minus 1, what we have here in the denominator. If I multiply the numerator and denominator by root 2 plus 1, then I will get root 2 plus 1 by root 2 minus 1 into root 2 plus 1, that is like a squared minus b squared, you get 2 minus 1. So I just get 1, right. And this is 1 plus root 2. So if you try to write it in proper form, then it becomes 2 plus root 2 minus 1. So I have written it as an integer, the largest integer that is less than or equal to it, plus something that is between 0 and 1.
Okay.
So if I do this now, what I will get is 1 plus 1 over, and now I have this thing over here, right, in the denominator, and so that becomes 2 plus root 2 minus 1. Now look, this is exactly where I had started off in the first place, right. So I can now apply this again, and I will get 1 plus 1 over 2 plus 1 over 2 plus root 2 minus 1.
Okay.
And in this case, because the process keeps repeating itself, it will never terminate. This will go on indefinitely. And so I can keep doing more and more terms in this expansion, and I can write 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus root 2 minus 1, and so on and so forth. Now, where is my sequence in here? So what I can do is I can just construct a sequence from this. So first I will take, let me write down the sequence in a different color. So A1 I will just take to be 1. So that is the first term. What I will do is I will just ignore this root 2 minus 1. It is something between 0 and 1. We will regard it as something kind of small, okay, and we will just ignore that. So if I ignore this root 2 minus 1 here, I get 1. If I ignore this root 2 minus 1 in this term over here, then I will get 1 plus 1 over 2. And over here if I do it, I will get A3 equals 1 plus 1 over 2 plus 1 over 2, which works out to be, so this is 1 plus 1 over 5 by 2, right?
Mhm.
So that's 2 by 5, and that is 7 by 5. And A4 is 1 plus 1 over 2 plus 1 over 2 plus 1 over 2, and that works out to be, it's our old, let's see, I worked it out before, I written it down here, it is 17 by 12. The next term A5 is going to be 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, and this turns out to be, let's see, I've written it down here. This is our old friend 41 by 29, and the next term A6 will be, let's see, 99 by 70. I've already worked it out. If you work this, if you look at what is 99 by 70, this is 1.4142857285728557 and so on. That's already within three decimal places are correct. Right? Root 2 is 1.4142. No, 4 decimal places are correct. So we get square root 2 up to 4 decimal places just using this. So here you get a sequence of rational numbers that converges to square root 2 using this very beautiful technique of continued fractions.
I see. So now I understand what you meant by saying sequences are useful to study real numbers.
This sequence actually, you can work it out. It has, you can compute an plus 1 in terms of an. I think the student should really try this. So what you can show is that an plus 1 is equal to 1 plus 1 over 1 plus an. This is a recurrence for this sequence here. And so you can quickly compute the terms of the sequence and get better and better approximations of square root 2. It's not quite Aryabhatta level, but it's a start.
I see.
So, here we had this number square root 2, and we were able to get numerical approximations to it using a sequence. Sometimes numbers are even defined in terms of sequences. I mean, the very definition of a number involves saying that it's the limit of a sequence.
What sort of number do you have in mind?
Okay, so there's this number E, Euler's constant, and this is in many textbooks it's defined as E is equal to the limit as n tends to infinity of 1 plus 1 over n raised to the power n. And you can use this to compute, get approximations to the value of E.
Why does this sequence converge?
Yeah, that's a good question. So let's see if we can prove that it converges. So we'll have to use the least upper bound property of the real numbers. We'll show that this sequence, so let's just define an to be 1 plus 1 over n raised to the power n. And what I'll try to convince you is that this sequence is weakly increasing and that it's bounded above. So we claim that an is less than or equal to an plus 1. Okay, so let's try this. So we have an. We'll use the binomial theorem to try to figure out what these things are. So let me just write down the first few terms in the binomial expansion of an. So an is 1 plus 1 over n raised to the power n. So if you look at the binomial expansion, so remember the binomial expansion of 1 plus a is summation k goes from 0 to n choose k, a to the power k, and this n choose k you can think of it as n times n minus 1, n minus k plus 1 divided by k factorial, right. So let's write this down. So the first term will be 1, Then the second term will be n choose 1, which is n. So I'll write it as n divided by 1 times 1 over n, right? This is the 1 a to the power k. Then the next one will be n into n minus 1 divided by 1 into 2, and here we'll have 1 by n squared. And the next term will be n into n minus 1 into n minus 2 divided by 1 into 2 into 3, and here we'll have 1 by n cube, and so on, right. So, similarly you can write a n plus 1. So, let me just, so it starts off with 1, then it's n plus 1 by 1, 1 over n plus 1. Then the next is n plus 1 into n. The denominator here is the same. Here we have 1 by n plus 1 squared. Then we have n plus 1 into n minus 1 divided by 1 into 2 into 3, 1 by n plus 1 cubed, and so on. Oops, cubed, and so on.
So when you say and so on, you mean they only have finitely many terms?
Oh yeah,
right?
yeah, it's an excellent point. So this will have n terms, this will have n plus 1 term. So this has 1 term more. This the thing for a n plus 1. No, sorry, this will have n plus 1 terms, and this will have n plus 2 terms. Remember, in this binomial expansion, the sum goes, k goes from 0 to n. So it has n plus 1 terms, and so this will have n plus 1 terms, and this will have n plus 2 terms. So most of the terms have corresponding terms. There is one last extra term in the second sum, and what we will try to do is just see if these terms, term by term, we can prove some sort of inequality. So let us look at the first term. Well, they are the same, right? And the second term also, we have n by n, and here we have n plus 1 by n plus 1. So that is the same, right? So let us just look at these term wise things. Now the third term, we have n by, so what I will do is I will write it like this, n into n minus 1. So these denominators are the same in both of them, we can just not worry about them. So maybe let us write it like this, the kth term in the first row, the kth term in the expansion of a n, what is it? It's, so I will write it in a certain way. So it's n into n minus 1, n minus k plus 1, and I will put this 1 over k factorial, that is what this denominator is. I will put it aside, and in the denominator we have n, and we have k factors, each one equal to n. So we can think of this as 1 over k factorial n over n into n minus 1 over n all the way up to n minus k plus 1 over n. The corresponding term for a n plus 1. So the kth term in the expansion of a n plus 1, what is that? So that is 1 over k factorial, and now we have n plus 1 over n into n plus 1 over n plus 1, right? Here we have n plus 1 power k, so n over n plus 1, and then we have all the way up to n minus k plus 2 over n plus 1. So if we want to compare these, we have to compare n. So if we look at the rth factor here, r starts from 0 and goes up to k, we will be comparing n minus r divided by n, and we will be comparing n plus 1 minus r, or n minus r plus 1 divided by n plus 1. So, factor for factor. It turns out, and this I leave as an exercise, that n minus r by n is actually just slightly less than n minus r plus 1 by n plus 1 for all r I guess I could take up to k. So, each factor in this kth term expansion of a n is slightly less than the corresponding factor in the kth term expansion for a n plus 1, kth term.
Less than n or
this is for r less than k, because there are k factors over here. And then we must also say for 0 less than or equal to k less than or equal to n. Okay, so it's you need to think it through carefully, but the upshot is that a n is actually less than a n plus 1 for all n greater than or equal to 1.
So, there is one extra term in a n plus 1.
That is right. So, that is anyway an extra term, and so it will contribute even more to a n plus 1.
Okay.
So, this sequence is monotone, it's in fact weakly increasing, and the other thing we need to check is that it is bounded above. So, I need to give a bound for a n. Okay. So, let us try that. So, again maybe we can just look at this yeah. So, yeah actually, so this thing, so how do I do it? Oh yeah, this is less than or equal to 1, and So, again if you look at the kth term in the expansion of a n, it is 1 over k factorial divided by n plus n minus 1 by n and so on. Now, all these fractions here, n minus 1 by n minus 2 by n and so on, these are less than 1. In fact, this one is also less than or equal to 1. So, what we get is that a n is well, it is less than or equal to 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial and so on, right. But what is this k factorial, right. So, we have this is 1 into 2 into 3 into 4 all the way up to k. This is certainly greater than or equal to 2 into 2 into 2, taking k terms, i.e. I guess k minus 1 terms, because this 2 is greater than or equal to 2, 3 is certainly greater than 2 and so on. So, here we have k minus 1 factors, each of them is greater than or equal to 2. So, this is greater than or equal to 2 to the power k minus 1.
Okay.
So, what we have is that this is less than or equal to 1 plus well, I can just write this as so 1 over k factorial is less than 1 over 2 to the power k minus 1. So, 1 over 2 factorial is less than 1, 1 over 3 factorial is less than half, 1 over 4 factorial is less than 8. Okay. And this is the series from my sad marathon story, right. So, this is less than or equal to 3. So, what we have is that the terms of the sequence a n are bounded above by the number 3, and the sequence is weakly increasing. So, it must have a limit, and in fact, the limit should be something less than 3, and that is Euler's constant, which is approximately 2.718, and it is the natural base for logarithms, which we will see later when we study calculus.